In the world of engineering, there's this really frustrating paradox. You've got these materials we need the most, the strongest, lightest aluminum alloys, but they're often almost impossible to work with. Today on The Explainer, we're going to find out why you can't weld the unweldable, and, more importantly, how scientists are finally cracking the code.
Okay, let's just dive right into the heart of the problem. On one hand, you have the 7000 series aluminum alloys. I mean, these are the superstars, incredibly strong, super light, perfect for things like airplanes. But you try to weld them and they have this nasty habit of cracking. Then, on the other hand, you've got the 5000 series. These weld beautifully, which is why you see them in things like ships. The catch? Well, they just don't have that same top-tier strength. So for years, engineers have been stuck with this frustrating trade-off.
So here's our game plan for today. We're going to start with that paradox. Then we'll deconstruct a weld crack to see what's actually going on. From there, we'll get into the cool stuff, how new alloys are being designed, how we can predict cracks before they happen, and what the future of welding is going to look like. All right, so let's really dig into why this problem is so critical. We're talking about the high-stakes world of advanced materials, where choosing just one alloy can make or break multi-billion-dollar projects.
High-performance aluminum is pretty much all around us, even if we don't always see it. The 5000 series, that's building our ships. The 6000 series is probably in the body of your car. But it's this 7000 series we're really focused on today. That's the elite stuff for things that have to be incredibly strong and light, like high-speed trains and spacecraft. And this is exactly where that welding problem becomes a huge roadblock to innovation.
This quote from the research really just gets right to the heart of it. It's not just that welding these alloys is difficult. For some of the most critical jobs out there, it's just flat out forbidden. I mean, think about that for a second. You've got the absolute perfect material for a new spacecraft, but you literally can't join the pieces together. That's the challenge engineers have been up against. To solve any problem, you first have to really understand it. So let's zoom way in and look at what's happening on a microscopic level when one of these welds actually fails. It's a pretty fascinating and destructive process. Okay, so the main villain in our story is something called hot cracking. Just picture what happens during a weld. You melt the metal, right? And then it cools down and shrinks. Now, if that piece of metal is clamped down and can't shrink freely, these immense stresses start to build up. And when the metal's in that fragile, semi-solid state, not quite liquid, not quite solid, it's at its most vulnerable, and it can literally just tear itself apart. And what's really fascinating here is that the crack isn't just one single event. It's actually two different kinds of failure happening at once. The most obvious one is right in the weld itself, in what they call the fusion zone, as all that molten metal turns back into a solid. But there's a sneakier problem happening in the metal right next to the weld. It gets just hot enough that the edges of the metal's internal grains start to melt, creating this weak, brittle network that just cracks super easily under stress.
So now we understand the enemy. How in the world do we fight it? Well, this is where it gets really, really clever. Instead of just trying to perfect the welding process, researchers decided to go back to the source and basically rewrite the material's DNA.
And here it is, the big breakthrough. For decades, the recipe for these high-strength alloys always included a high ratio of zinc to magnesium. But scientists discovered that if they flipped that recipe, using more magnesium than zinc, it fundamentally changed how the metal solidified. So why does that work? Well, this tiny chemical tweak actually stops a brittle, low melting point film from forming between the metal grains as they cool. And that film is exactly what gives cracks a perfect little highway to tear right through the material. And the data? The data proves it works, big time. A standard weldable alloy, that 50,000 series, has a strength of about 144 megapascals. That's just a unit of pressure. The unweldable 7,000 series is way stronger at 392. But now, look at the new alloy in the middle. It welds perfectly, and it has a strength of 404 megapascals, even stronger than the original. They didn't just find a compromise, they actually created something better. This chart just makes the achievement so incredibly clear. That new alloy isn't some middle ground compromise. It completely solves the welding problem, and it's even stronger than the old unweldable version. This is what a real material science breakthrough looks like. Okay, so how do scientists test these amazing new materials without just doing costly, massive trial and error experiments? I mean, you can't just weld a whole airplane wing to see if it'll crack, right? They needed better, more precise ways to actually measure weldability.
And that need led to some really clever new testing methods. We're going to look at two of them, the circular patch test and the more advanced controlled tensile weldability, or CTW test. And these aren't just pass-fail. They let researchers put a precise number on just how resistant an alloy is to cracking. So this is the circular patch test, and the idea is simple, but man, it is brutal. You take a plate of the alloy, you clamp it down so it absolutely cannot move, and then you weld a circle right in the middle. As that circular weld cools down and tries to shrink, the clamps resist, creating these insane levels of stress. It's basically a torture test designed to find the material's absolute breaking point. The CTW test, though, is even more sophisticated. It uses these incredibly precise instruments to measure the exact amount of strain on the metal as it's being welded. So this isn't just a simple pass or fail anymore. It allows scientists to create these super detailed maps showing the precise boundary line where an alloy will crack versus where it'll hold strong. This is predictive power on a completely new level. Of course, in science, solving one huge problem often just reveals new, more subtle ones. So while these are massive breakthroughs, the quest for the absolutely perfect weld, well, it isn't over yet. So the next frontier is all about purity and structure. For example, even tiny amounts of hydrogen gas can sneak into the weld and cause huge problems. So now researchers are looking at ways to trap it with elements called getters, or even using special shielding gases to purify the weld on the fly. And at the same time, they're adding things like scandium to refine the metal's internal grain structure, making that final weld even stronger. So what's the big takeaway here? We are making the unweldable weldable by combining two really powerful ideas. Going back to the fundamentals of metallurgy to literally rewrite the recipe, and then using advanced testing to prove that the new theories actually work. It's this one-two punch of deep science and smart engineering that's unlocking the materials of the future. And that really leaves us with a final thought. We've cracked the code for high-strength aluminum. But as we keep pushing the limits of science and engineering further and further, it really makes you wonder, what other seemingly impossible materials are just one big breakthrough away from completely changing our world?